Okay, welcome everybody. So this is going to be a shorter talk for us, our short paper on the subject related to the first talk we had today about automation, and more specifically in this case in Isabelle Hall also. This is joint work with Jasmin Blanchette. And we'll start with a small summary of the proof automation in Isabelle Hall. So most of you will probably be familiar with this. This is just to introduce the terminology that I will be using. So we have the concept of a proof method, and a proof method is some kind of algorithm or heuristic that you can use inside of Isabelle. So it's an internal tool that will try to automatically solve or simplify your proof goal. Examples of those include SIMP, which is some conditional equational rewriting. Auto adds some classical reasoning on top of that. BLAST is some Tableau prover. METIS is some power modulation prover, and so on. So those are the tools that Isabelle users are using every day in order to write their proofs. Now, the problem with them is that you have to know that they exist, you now have to remember their name, and you have to know when you should use which one depending on what you're trying to prove. This is a lot of work, and since we are lazy, we have some tools to try to do that for us. The simplest of those tools is called try0. It's basically a push-button automation which will try all of the existing and registered proof methods in parallel, and then will report you on the one that succeeds, and you can copy-paste, or more specifically, you can just click on the result, the one that you like, and then it will be inserted in your proof text. But there is some more powerful automation. In this case, in Sledgehammer, it's called Sledgehammer. Sledgehammer is our version of what is called more generically a hammer, or ATP hammer. So it's also some push-button automation, but it will use external automatic theorem provers, so ATPs, in order to try to solve the goal. And if this works, then it will try to construct an Isabelle proof out of that. The main components are some relevance filters. So Sledgehammer, or a hammer in general, is going to look at the theory, at the existing definitions and theorems that exist, and will try to guess, based on heuristics, which one could be useful for an external ATP to prove the statement. Then there is a translation module to translate from the internal Isabelle representation to whichever language the external tool understands. And then there's the call of the external ATPs itself. And if the external ATPs report that they found a proof, then there is a process of proof minimization, because, of course, many facts were provided to ATPs. Most of them are probably not necessary for this proof. So we try to figure out some as small as possible subset of the facts. And then based on that, there is an internal proof reconstruction in Isabelle to try to display an Isabelle proof to the user. So those are the tools that one is used to use in Isabelle. From a user's perspective, it looks a little bit like that. So we can call that automation-driven development. So as a user, I basically state the proof goal of what I would be interested to prove. Then I start to use the automation. So I usually start with try0, see if it's an easy goal to prove. If that doesn't work, then I will try Sledgehammer, and then wait a little bit. And if an external ATP is able to solve it, I'm happy. I have a proof, and I can go on and do some other things. Otherwise, well, I will just search for an intermediate lemma that could help automation, and then go back to step one and try to prove this one using automation. So this is what one way of proving formalizing stuff in Isabelle looks like. But there are some problems with this. So one of the things is that try0 and Sledgehammer have different strength, and they can prove different things. So one does not subsume the other. So that means that you have to manually call both tools one after the other, which is manual work, which I don't like to do. And another thing is that try0 is quite limited. So it's a very simple tool, and I have to manually provide the facts that I think could be useful to solve the proof goal. So again, this is manual work, and I don't like to do that. So the goal of this project was to try to alleviate those caveats and try to find a solution such that the user can just push one button, wait, and then get all the results that are possible by doing all of this manual labor here. And our solution to do that is to use an ATP-free architecture for a hammer. And so you remember those are the components of a hammer that I described previously. And what we did is that we basically tuned those a little bit. So the relevance filter is exactly as before. There is no change there. There's no need for a translation module because the proof methods already know and understand Isabelle's internal representation. And then the external ATPs are replaced by the internal proof methods from Isabelle. The proof minimization is as before, there is no change there. And there is also no need for proof reconstruction because the proof reconstruction would basically use the proof methods to try to find a proof. So since we already use those proof methods for the proof search, if that worked, then we already have something that is acceptable for Isabelle and you can display that directly to the user. So in this project, we implemented this new architecture for ATP-free hammer. And the way we can use it is this way. So this is an example of a problem that we found during the evaluation of something that's an example where this new architecture actually adds something compared to the status quo. So if we look at that very quickly, we can see this is basically the associativity of the map2 operation on list for some binary operation of abelian semigroup where the operation is additive. I don't remember exactly from which formalization this comes from, but this was just something that was in the middle of a big proof where the user realized, oh, the automation doesn't work, so I should probably add something, some nice lemma in the between, and this is the lemma that the user found. And this, I found that verbatim in a formalization somewhere. So if I was to try to prove that as a user, well, I would start my automation-driven development. I will first try 0, the command try 0. It would time out after a few seconds with no proof. Then I would try to call the ATP hammer, so Sledgehammer. It will also try time out after some time with no proof. But when using the ATP-free hammer, then a proof is found, and it looks like that. So it's a bit ugly because of the number of facts that were necessary and of the long names, but this is fundamentally a very simple proof. So it's just using simplification with a certain list or set of lemmas that I would never have found out of the top of my head. So this was only found because of the fact selection of the ATP-free hammer. So this is what we aim to achieve. And ideally, all of this would be performed automatically in just one command so that I wouldn't have to write all of those calls or perform the calls to those tools manually. Now, we have only at least one example to show that we have achieved something that was not possible previously. So this is the contribution, non-zero contribution. We can be happy about that. But the open question is there more success than just this one? And to do that, we did an experiment where we selected 20 formalization from the Isabelle distribution and also the archive of formal proofs at random. And in each of those, we selected 250 goals. So that means a total of 5,000 test cases. And we tested many configurations of the proof methods on those test cases, more specifically 13 proof methods. We use a 2-second timeout. So this is the confirmation from the first talk today that we use in Sledgehammer, a very short timeout. This is actually twice the timeout that we use in practice because we wanted to, for the experiment, to give a little bit more time to the proof methods so that the hope that it would provide some more stable results from one to the other. I can also confirm that this is the case because 95 to 99% of the proofs were found within 1 second. So the supplementary seconds is really just for a few percent of the found proofs. And we tested with a different number of facts, scaling between 0 and 64. And I want to stress the fact that testing all of those proof methods with 0 fact, this corresponds exactly to what try 0 is doing. So when we test all of that, we also test try 0 at the same time. Those are a few results of the best performing proof methods that have all more than, I think, 10 or 12% at their best situation, their best number of facts, which is always somewhere between 8 and 16, if I see that correctly. Yes. And what we can see is that in contrast to external ATP proofs, Isabelle's internal proof methods are not very good at handling many facts. So this is probably the minimum amount of fact that we would give to an external SMT solver or ATP. But for our proof methods, it's already way too much. So they go in the order of the automation driven development by first trying try zero, which is all of the proof methods without any facts. Then we would get a success rate of 29%. By calling Sledgehammer, the ATP hammer version would get a success rate of 72% approximately. And if we were to call just the ATP-free version of the hammer, we'll get a success rate of 46.1, so which is way lower than the ATP hammer. So we could first say, oh, that's bad, it doesn't work, the success rate is much lower, let's throw that out of the basket. But that's not the case, because those proofs that were found were not exactly the same. So if we take the union of the solved problems, for example, what we can already do manually, but by calling the commands one after the other, so the first calling try zero and then calling the ATP hammer, we get 74%, which is 2 percentage points higher than just calling Sledgehammer. So not being lazy and actually calling the second commands is already useful. So we get 2 percentage point more problems. But also, if we call the ATP hammer and the ATP-free hammer one after the other, then we get a slightly more, like 0.5 percentage points more problems. So a slight improvement. And remember that this one, so the ATP-free hammer, includes the try-zero. So there is no need to perform a test of the ATP hammer, the try-zero, and the ATP-free hammer, because the try-zero is already in this one. So the conclusion is that calling the ATP hammer and the new ATP-free hammer does improve the success rate for the user. And that's what we did in this project. We implemented and evaluated the ATP-free version of the hammers. It can find new proofs, and we integrated it in Sledgehammer. It's going to be in the next version, soon to be released this year. And concretely, what this means, so the take-home message for Isabelle users is that you can stop to use try zero before calling Sledgehammer, because now it's done automatically for you. And you can expect in some situations some better results. So if you only need to remember one thing from the talk, it's this one. You can forget about try zero and just use Sledgehammer. All right, starting with the next version of Isabelle. And that's it. Thank you very much.